Mr. Crispin here once again, and welcome to my workshop. In today's video I'm going to be working on a precision lap to lap the piston valve bores of my locomotive cylinders. Now today's work will be very much based on the lap rather than the cylinders, and I'm going to be making something along these lines. Now the work in today's video is inspired very much by Robin Renzetti, and if you have a look at his video making large diameter laps you'll see the kind of thing this is based on. However, make sure you finish this video first. Now what we can see here is a steel shaft, an aluminium lapping head, and then an adjustment screw in the end for controlling the expansion of the lap. So I won't go into too much more detail now. We'll start off with a piece of steel and start work on the shaft. I've been rummaging around in a box, and this appears to be the most suitable shape material I can find. The only thing is, to my eye, it looks a little hard. It appears to have a kind of hardened surface, so let's have a little go at it. Maybe not. Yeah, seems doable actually. I'm just mindful I'll at some point have to cut a or tap an M4 hole in this stuff, so I don't want anything too bad. Now perhaps I'll hacksaw it all the way through just to make sure there's no surprises in there. I want about seems pretty consistent all the way through, although it's definitely got an element of toughness to it, so I'll just have to see how I go on with that small hole. Anyway, let's head to the lathe and begin. The approach I'm going to take today is to just use a range of work holding methods in this lathe just to get it roughed down, and then once I've done all that I'll hold it between centres and finish all the key geometry in one setup. That is generally more efficient than trying to maintain good alignment across all the ops through multiple work holdings. So for now this is purely roughing out, and I'm going to face off and put a centre in. Now the machine is currently covered in cast iron dust, so rather than use the flood coolant I'm just going to brush oil on for today. And let's see, let's go for 490. I think there's a good chance that's the roughest piece of material that's ever been seen on this channel. I'm starting to think this should have stayed in the box. Anyway, I'll proceed. So that is the diameter turned down. The reason it's gone to such a small diameter is that A, I have to hold this in a chuck somehow, and B, I need enough space on this shoulder to get two small cap heads in there to hold the lap in place. But that will do the job fine. For those interested, let's see how much deflection I've got having no steady. One and a half thou to the middle, 2 thou at the tail end. So proof that if you were doing something precision you would need a little more care and forethought than I've used in this example. Okay, I will now reverse this piece. The Dave Ticehurst sliding tapping chuck is making short work of this. I've been in there with the taper tap, and I shall now finish off. the tap just slides in on that diameter, and by use of feel you can tell how much force is being applied. That's it. Now, in case you've never seen this before, I do have a video on it, but basically it's just a DIY type screw-on chuck with a bolt and lock nut firmly mounted in the back, with a ringed hole then put down the middle such that it can slide on the guide rail. And I use this a lot on the milling machine, but also here on the lathe. Okay, so that is the basic rough turn shaft, and I'm going to finish this off on the Myford between centres just because they're nice and small and allow good access. Also, I'll be interested to see how a nice sharp high-speed steel tool does on this material. Quite often these unruly surfaces prefer that kind of a sharp positive rake as opposed to these sintered negative rakes, particularly with finer cuts. So I'll do that. I think the last thing I'm going to do before I do that, however, is just take this to the cone lapper and give the cones a tart up, seeing as I've been tapping, etc. This machine has been mistaken in previous videos for either the world's most poorly placed pillar drill or something for polishing cones. Neither is actually true. What it is a Jones Shipman Cone Lapper, and it's designed to accompany a cylindrical grinder. So this machine is really made for high precision work and also hardened steels, and the idea is after your part has been heat treated, you lap the cones to get them in line, round, and all sort of geometrically correct. Cone lapping is associated with giving parts a high degree of roundness in cylindrical grinding. So in cylindrical grinding, the rounder the cone, the better contact with the centres, therefore the less bounce you get, and the rounder the diameter. I'm using it for completely the wrong purpose here, which is just to deburr the cones, but I might as well show you while I'm at it, so here goes. So now when that goes onto the centres in the between centre setup, everything is bang on in line and the cone geometry is in line with each other from both ends. Okay, between centre setup on the Myford lathe complete. What I've got here is a razor sharp carbide tool, positive rake all round, and I've lapped all three sides. I'm expecting that to give me a better finish on this piece of material than the sintered negative rake, as typical with those kind of inserts I was showing earlier. Now I'm going to do this in a two-pronged attack again, and up to this black line to the end is going to be the chucking diameter, and I'm going to turn that to exactly 3/8 of an inch so that I could hold it in a collet in the future, and then the rest of it will be the geometry required for the lap holder. So that's that. Much finer finish, that's good. So there is the shaft. Now what was particularly interesting about that was the difference in surface finish between the two lathes. Those of you watching in HD may have noticed that from the Harrison lathe I was really getting quite a coarse surface finish, and that was with the sintered carbide insert. Over on the Myford I was using a carbide tool again, but this time one that was actually ground and lapped to a sharp cutting edge. So if we consider the differences, both tools are made of carbide, both spindles were doing approximately the same speed, both work holding setups are very similar, and the material of course was the same. The key difference was the geometry of the cutting edge. So let's have a little closer look at those cutting geometries. Here is obviously the bigger sintered carbide insert. So that's carbide, but it's created by a pressing motion and a heated sintering. So that's that. This is what you might call a more traditional just ground, or in this case ground and lapped cutting edge. In short, these aren't actually very sharp. You can't really cut yourself on it, and they slope up, meaning negative rake. These are a lot sharper. You probably could cut yourself, and they slope away, positive rake. So what's the difference? Well, basically this puts more force into the workpiece as it's cutting. This is doing more of a peeling motion, like a sharp knife going through butter, whereas this is doing more of a pushing its way through motion, a bit like digging butter out with a spoon. But certainly for modern CNC or aerospace materials or high spindle speeds, these hold up better because they aren't razor sharp, so they don't lose their edge, and in the case of a rigid machine and a good machinability, the material can cope with the slightly bigger force this puts in. What my component demonstrated today, however, is that when you are on manual machines with a bit more play and the material isn't very happy, the tool that puts the least pressure into the work gives you the best results, particularly with a nice sharp edge and some oil. So that is an interesting thing. There are an awful lot of caveats to what I've just said, and one of the main skills in, say, turning is spotting the things that are going on that allow you to pick between these things. But if you're new to machining, the main takeaway is don't assume that because it's a high grade holder and an expensive Sandvik insert that it's always better. It's well worth having some sharp positive cutting geometry up your sleeve for times when you need it, particularly on a machine like a Myford, where it's not got the inherent rigidity and weight behind it that you need to keep one of these inserts stable. Sometimes I do use this on the Myford, a sintered insert, but what you can't always see is that I tend to lap them to give them a sharp edge. On to making the lap. I am now going to use a cutter to create a counterbore into the face, and there's a couple of things to point out. First of all, please be aware if you're ever using a cutter to create a counterbore, just note that the bottom will not be flat. You can see that just about every standard cutter has a roughly sort of 2-degree back angle on it. That's the first thing. The second thing is, how do you go about producing this to a depth? Well, obviously if precision depth is required, then some kind of boring or clocking system could be employed, but as far as using the tailstock for its plain and simple operation goes, here's a little trick I have come up with. I am basically just going to rely on the tailstock quill, hence why I mentioned other alternatives should you need more accuracy, but basically I'm going to bring this to a known size in the direction I'm going to travel. So let's bring it to exactly 10 mil. I'm on the line there. Now what I'm going to do is bring the saddle up to the tailstock, and then going to push the tailstock against the saddle, and now with me pushing on it, the two move together. So what I can do is start the machine up, So having used the saddle to give me control, I made contact with the face, locked the tailstock in position, backed off the quill and then wound off. Now as I wind back in again, the cutter should make contact with the face just as the 10mm line appears on here. Therefore if I want to feed another 10mm, I'll wind another 10mm and that should work. Right, the last step there was to go in with a small end mill and to true up the drilled hole. That drilled hole will be the seating diameter for the adjustment screw, so I at least want to make sure it's concentric, and going in with a milling cutter should have trued that up. That is all the internal work done for this op. What I will now do is put in the axial and radial slurry grooves, so a series of grooves down here and then a series of grooves going along the part. That will help the slurry get round the lap, and following that I will part off and take this to the collet chuck in the Myford and do the other face and produce the pilot bore on the other side. Yep, they look deep enough. I'm now putting in my axial grooves, and I've done 12 o'clock, 6 o'clock, 3 o'clock and 9 o'clock, so I'm just picking positions with this jaw. It looks to me like I want probably quite a few more, so let's see. If I now do the same with a different jaw, I should get a pattern offset by a third. So let's do 12 o'clock, 6 o'clock, 9 o'clock with this jaw. That looks like it will be about right. So I'm just doing this in the 0.1 depths. Plenty of cutting oil. I have now got the piece the other way around in the Myford collet chuck, and I'm going to just finish it off. Well, you've heard quite enough of me for one day, so I'll call it there. In the next video I'll be doing some drilling and cutting to make this an expanding lap. I'll be adding the screw from this direction and two from this direction to hold it all in position and give it its expanding feature, and then I'll be truing it all up to make sure that it's round at its operating size. I will probably then create a test bore in some cast iron and do a bit of an experiment. So I hope you found this interesting. Thank you for watching, and see you on the next video.